All right, welcome to 4.2. We are going to start now talking about, instead of nominally static fluids, moving fluids, fluid dynamics as part of fluid mechanics. And so a couple of examples of this are the jet lev, which we'll use on multiple occasions, which is kind of I think it's a $150,000 toy, but you can see exactly how it works. It's basically a fireman's hose, which is run on an umbilical from a little float that you pull behind you with a motor in it, which pumps up a pressure in a. I should probably put this down. I'm fighting against this. Pumps up pressure within a hose, and then squirts it down on the water surface, or solid surface for that matter, to be able to elevate you. And so that's one of the things that we'd like to be able to deal with. Let's also put this down to mute. Maybe that's not the one I'm looking for. Maybe it's... Of course, we're all lucky, including me, that we survive our youth. And so I guess Jackass is a kind of take on that, as you can imagine. So this is actually quite similar to the previous one as well, right? So the so-called fire hose rodeo. But certainly that's something that we could analyze, or should be able to analyze, with the information that we have available to ourselves. And other related components. Again, let's see how this works out. See if we could have to deal with a bunch of advertising on this. But boats, planes, many of the things around us which get us around from location to location, including things that we might use not just for transport, but just for sport. So this is an amazing evolution, as far as I can see, of America's Cup boats, which have probably been a race that must have been around for 100 years by now. Originally in 12-meter yachts. 12 meters, I don't think, is the length of the yacht, but it's some formula of different lengths that go together, to the current form of what America's Cup boats are these days, in terms of these catamarans or trimarans that also have hydrofoils, wings underneath them to be able to lift them out of the water, to be able to reduce drag. And of course the sails, which really aren't sails as we think of them. They're moderately rigid, probably made of Kevlar, which are used to basically act as wings. Not so different from airplanes. And so those are the kinds of things that we'd like to be able to understand, and we'll try and understand in this class as we talk about fluid dynamics. And I don't know where this is. Oh yeah, this is the right one. And we've used this in the past as well. So this is an airport, kind of interesting. It's a dramatization. I think they'll make the point during this. Perhaps they say it. I think they show it on here as well. But it is a common scene running around an airport. This happens to be, I think, as we'll see it, is SFO, San Francisco. And it's a dramatization, basically health and safety dramatization, to encourage people maybe not to drive behind planes getting ready to take off. And so this is an old truck that's towed behind it. From that view, it looks like it's SFO, one of the few not the only airport that sits kind of on an island that's artificially created. There's many of them. I guess Hong Kong, Kansai is exactly the same. And just run that back again. Made on a dredged island. So this is, pretty sure that's San Francisco, for which is a United hub. This is the old livery colors for United. And making the case that if you're driving around on taxiways, don't go behind a plane that's about to take off for obvious reasons. And so those are the kinds of things that we'd like to be able to deal with. Stage demonstration, professionals, don't do it at home, don't repeat. And you also see these, I'm sure you might in your lifetime watch YouTube once in a while, you see these people hanging onto the fence behind the airport in St. Kitts as planes take off, and people going horizontal as they hold on to things. And another form of maybe not so jackassish, but just reality that there's a lot of wash from there's a lot of power when you have to get something that weighs I'm not sure what a plane weighs, a few hundred tons off the ground, which, as other comedians have commented, is slightly denser than air, right? When you look at airplanes. And so that's kind of what we'll talk about today. And so we're moving on from talking about fluid statics, if you like, to talk about fluid dynamics. Really, 4.1 is also fluid dynamics as well. You could think of it, but this is the main. But this is the main entry into it. So, as we've done before, what we'll do is we'll kind of recap a little bit about what we talked about last time that led us into this, and then take it from there. And so, the last things that we talked about, you'll recall that we had looked at using Newton's second law, always, F equals ma, both in linear form, F equals ma, and in rotational form, F equals m angular acceleration, which is v squared over r, that acceleration. And we'd use those expressions to be able to derive the forces that get applied on static fluids which are accelerating. The fundamental relationship that we used was, for at least in the linear case, you'll recall, was something like change in pressure with elevation minus unit weight minus density times acceleration in the z direction was equal to 0. That was the expression that was the font, the original kernel of everything that we developed. We made the point that this really, if we divide it, is really, at least in terms of forces in the z direction, equal to this. And from that, we could play around with it to do the things we talked about last time. So two of the things we talked about last time were to be able to figure out what the inclination of a slope, surface slope, would be within a tank if we accelerated this tank at some acceleration ax in this particular case, or az vertically, where our coordinate system was x and y and z upwards. And basically we discovered that the slope of this curve that we could get, which is given by this inclination of this plane, would conform to this. It came exactly from this, just from being able to figure out that on this upper surface there'd be no pressure change as we moved along this, and this would be the location that it would reset itself. In addition, so that was one result that we got. I think we called it 1 last time. The second result is, what does fluid pressure look like as you go down within this? And we noted that just like in the case for a static fluid, because of this term here, the fluid pressure would be linear. But if there was an acceleration vertically upwards in the z direction, then gravity would be augmented by a certain amount, and the pressure would still be linear, but it would be steeper, less steep, maybe less steep. Larger pressure at depth if you're going up, as you can imagine, an elevator. Smaller pressure at depth if you're going down. So those are the standard results that we got from this. The corollary of that was that we then looked at it for a rotating fluid, and we came up with a similar outcome, I suppose, just to use the same colors again. If we rotate a fluid around an axis, where this is the center line that we rotate it, then if it has a free surface, then it has some distribution. where the elevation of that height, I guess z, depending on where we take our, this would be radius, this would be the z direction upwards. The elevation of z would vary with r, and it would increase as we go out, as we, according to this. And this is the angular acceleration in radians per second that we rotate this with. So same behavior. You're pushing something out, it's trying to get away from you. The only way it can do that is to stack up on the sides in response to it. That's what it's doing here. That's what it's doing here. If we looked also at the fluid pressures with depth, then conforming to this being the relationship for elevation relative to the radius, the fluid pressure with depth at any given radius, if you choose it, the only thing that changes is z. And so you'd expect that, say, if you looked on the corner of this bucket, then the pressure distribution at any depth is given by this, which is quite familiar to us, right? And again, it would respond, if we put it up in an elevator, it would respond in exactly the same way that this would then be slightly larger. It would be increased by some magnitude of the effective acceleration, but we didn't deal with that point specifically, but that's the deal. And so those were the two standard results that we talked about last time. So those were accelerating fluids. And so we used this to be able to make the case that Newton's laws are really what govern what is going on. So F equals ma is the cardinal rule. I guess also applying to this is that any object, if not acted on by other forces, will keep on going at the same velocity. And so that's true here. If I take my hand away, it drops because of gravity. If I threw it to you, then it would slow down because of drag. That's a force that's acting. And it's those forces are the only things that change that. And that's true for this ball, but it's also true for water, which would just be related to that. So the other thing that we could do is, and what we'll do today, is we'll talk about moving fluids. And so typically when we're talking about moving fluids, what we might want to do, for instance, is apply it to, say, something we know. I'm not sure what that looks like. Does it look like a tear? But it's an airfoil. And so if you imagine us having fluid that goes across here, then you probably met Bernoulli before. You know that we can write this equation, which is fluid pressure at a point plus its elevation plus its velocity head is equal to constant. After our friend Daniel Bernoulli. And I'll make the point that for this ball, that if it was moving across in front of you, we've used that to be able to, the concept of that, to be able to say what happens to the fluid pressures within this, if it's a tank. So if you imagine a tank full of balls moving across you, the fluid pressures you'd have would be this. But your frame of reference in looking at this as it moves across, as it moves across the room, is to keep your eyes on this and to think about yourself being attached to it, the accelerations that this ball is going through. When we talk about moving fluids, we're thinking about the same kind of behavior. The ball happens to be at this location at some time. Sometime later, it's at a different location. Sometimes later, it's at another location. The forces that should be acting on that ball would be exactly the same as if we're moving it across the room. But our frame of reference for fluid dynamics, if you like, is to take this streamline and to be able to sit statically and to watch this ball move across my face and out the other side. And so it's kind of a frame of reference issue that we're dealing with. So it's not surprising that we might be able to get Bernoulli's equation directly from looking at these equations from an accelerating fluid, directly without doing anything else. And so that's what we're going to attempt to do today, is to make the case that we can define this relationship. And you might note before we go ahead that this relationship for Bernoulli, pressure head, elevation head, and velocity head, has three terms. Rate of change of pressure, rate of change of elevation if you multiply this by unit weight, and a rate of change of velocity, which is what an acceleration is, right? dv dt is a rate of change of velocity with time, that these terms are exactly the same. And so if we wanted to, we could also think of this as kind of like this. And that's what we'll attempt to do. Okay. So there's nothing different in what we'll do today related to what we've, the foundation that we've established for ourselves already, but we'll just take that to the next stage. Okay. So what we'll find out, okay. The other point that I'll make is that there's a certain symmetry here. And the symmetry is that we've looked at linear accelerations. Where's my ball? Oh, there it is. Linear accelerations, and we looked at rotational accelerations, right? The forces this applies on the outside of the radius is pulled centripetally outwards. And so we've done that for static fluid in terms of these. It's gone down there again. It's not so difficult to believe that when we look at fluid behavior, we can look along a streamline, which is the direction here, which in the book they'll call S, and also normal to that streamline, which they'll call N. So along and normal. And you can imagine that the forces that you get are kind of the same thing. It's moving along. It's a packet that happens to be moving from one location to another. It's moving, if you go along a streamline, as this thing goes across the top of the wing. So if you imagine this going across here, then there'll be a parallel flow line here. This is really just like slinging a fluid around on some kind of radius that we talked about before, and it goes through at some angular velocity, and this is v theta in this direction here. And so the behaviors as you go normal to a streamline are really not very different from the static case either. So I guess I'm making the point that there's a certain symmetry between what we'll talk about today in terms of fluid behavior along a streamline, and also what we'll deal with actually tomorrow, Friday. Actually, we won't. I'll send you to the video because we'll have a review, but in terms of behavior normal to a streamline. All right? So that's kind of setting the stage. What we'll end up doing is we'll end up with these relationships. These are both along a streamline in a differential format. Whoops. And this second one is actually, I always write it as pressure divided by unit weight plus elevation plus velocity head. Which is exactly the same as this. I guess if you manipulate this, you can get it in that step. This is the first term, this is the second term, this is the third term. Just slightly moved around. But these are the two things that we like to be able to evaluate. Okay? And so we'll end up, that's where we'll end up. So Bernoulli equation, that's what we'd like to be able to figure out. It's for inviscid fluids, fluids for which the viscosity is 0, which really means that fluids for which frictional losses due to flow are very small compared to the other forces which are involved. And since you know that the other forces that we're talking about really relate to Newton's second law, the main forces would be the two forces which go into this, which would be pressure and elevation. Starts off here, it has some energy, drop it, clearly has some energy attached to it. Pressure, if I apply force to it, it moves. And on the other side, this is what you might think of as inertia. So if it's happily going along and no forces are acting on it, that's fine. If you have a stream tube, for instance, that contracts, and therefore to get the same amount of fluid through that contraction, just like a traffic jam, it has to go faster, then it has to accelerate in space. It has to accelerate, then you have to act against inertia to do that. And that's what this v squared over 2g term is. This is z, and this is p over unit weight, which is just these two terms. P not rho. Okay. The usual requirements for Bernoulli are these. The fluid has to be incompressible, but we use it for air, and air is anything but incompressible. It seems to work relatively well. That the flows don't have eddies in them, which is irrotationality. That it's steady. And so if you're looking at flow around this wing that we talked about before, the fluid velocity may be different here than it is here, but if you look at this picture at any particular time, the fluid velocity here is always the same at time 1 as it is at time 10, as time 100, bless you, and likewise here. Don't have to be the same spatially, but they have to be the same in time, which is what steady means, and that the viscosity should go to 0, or that these are nearly met. We'll see that we certainly use these behaviors in systems that are for air, which is not incompressible, and we certainly use it for water, which has viscosity to it, and so it just depends on the relative magnitudes of those terms as to whether it works or not. So for instance, if you look at flow across a weir with eddies on the downside and water, we'll certainly use it for that, and it works quite well. Places where it doesn't work would be in petroleum reservoirs or in groundwater reservoirs, where there are very large amounts of viscous forces which provide drag, and therefore mu is nowhere near equal to 0 because of the effects of trying to push itself through small pores. And so there are cases where it doesn't work so well. So that's kind of the background of where we're going. There's a nice derivation in the book. I don't want to use it, so I'm going to do something else just because we can. And so we'll work from this. Right. So that's where we are. So let's. So what I'd like to do is talk about fluid dynamics, and in particular, our good friend, who will become a good friend, Daniel Bernoulli, who apparently is from a large family of very prolific scientists, Swiss scientists maybe, of which we only know Daniel's name. And so, coming back to our case from before, what could we do? What happens if we take our coordinate system that we've had before, which has this z acting upwards, and we take two little packets of water at two different locations, 1 and 2, and we look at what the behavior should be on that pack of water, which is this. And so, without rederiving it, we know that the static equations, what we've called the static equations, are, just identified them, change in pressure with elevation, unit weight of the fluid, density of the fluid times its acceleration in z, and that should be equal to 0. Hopefully you believe that. We spent a lot of time dealing with that. We know that the first two terms are forces. We know the third term is inertia. What we could do is we could write this term AZ slightly differently. Acceleration is equal to what? It's a change in velocity with time. Which is equal to a change in velocity with time multiplied by 1. We know that this expression, by definition, is a velocity in the z direction, if we want. All our velocities would be in the z direction. And so we could rewrite this as equal to change in velocity with z multiplied by velocity. And we can also write that, if you remember, as equal to a half dz v squared. You could take that on trust, but if you don't take it on trust, then we can also do that. So what's that? So half change in v squared. Again, we can multiply that by being equal to a half this. We can write that as a half multiplied by gathering terms change in velocity squared dv multiplied by dv dz. And if we do this differentiation here, then this differentiation becomes what? 2v, this becomes 2v over 2, which is just equal to v. And I know we've lost this other one here, which is exactly the same as this. So in other words, this is actually equal to v over dv dz. So this term here is this, and so all we've, I guess, made the case is that this term really is an equivalent substitute for this, because we're able to move between them. And so what we could do is we could go back to this previous expression, and I'll go red again, to be able to write this including this new term. And so it's minus change in pressure with elevation. This is unit weight, but it may be easy to write it out as rho g. And minus density multiplied by what acceleration is. And we've shown that acceleration is equal to a half rate of change with z of v squared. Bless you. And that's equal to 0. And so what we could do with that expression is we could manipulate it in some way. I suppose we could multiply it by dz. And if that's the case, we get minus dp minus rho g dz minus a half rho v squared. We could integrate this. This is one form, okay? So let me go back to this. So we could now, if we wanted to, we could integrate this. We could integrate this And we don't need to do that here because it's already in that form, which is equal to 0. When we do this integration, this becomes a constant. And the integration of this is just minus p minus rho g z minus a half rho v squared equals a constant. And if we want to, we could divide through by gravity, divide through by density and gravity. And if we do that, then we have a final relationship which is getting rid of the negatives. Constant, which hopefully you'll recognize. So the idea is that we end up with an expression in two forms. This is Bernoulli as we think of it. Regular Bernoulli, if you like. And we can also define it in terms of differential form, if we so wish. May be convenient to look at it in this form. Of course, we could get rid of these as negatives and just make them pluses because it's equal to 0. And this is differential. Oops, got a time lag in it for some reason. So those are the two expressions that we will use. And so you don't need to derive them. You'll never be asked to derive them. You may want to use them. You will want to use them. But you need to realize where they're coming from. And just to reiterate again, the part that's due to pressures acting on the system or forces are the first two terms. The part that is the acceleration that you have to apply a force to be able to move it. If I throw this, I apply a force to it to accelerate it. So it's F equals ma, and it's nothing other than that. And so it's useful, I think, to view things in that context. Since this term is constant everywhere along a streamline, if we move the ball from point 1 to point 2, then usually what we do, as you all know, we will write the pressure head at point 1 plus the elevation at point 1 plus the velocity squared over 2g at point 1 is constant, but it's also equal to the magnitude of the pressure head at point 2 plus the elevation at point 2 plus the velocity head term at point 2. This is the essence of what we'll do. I mean, this is Bernoulli. You write it at one point, you write it at a second point. They have to be along a streamline. You hope that in writing it for those 6 terms, you know 5 of them and you don't know one of them, and you solve it. And that's the essence of what we'll do. Nothing more than that. So I'll just reiterate, you will not have to derive that, but it's useful, I think, to go there to see where it's coming from, because it's really just an extension of what we've already said about forces acting on structures. An exposition, if you like, of Newton's second law. So what do I want to do now? No, good. We're in good shape. We're all in good shape. Oh, I guess I want to do this. So let's go back to where we were before. So what we've done is we've taken care of, well, you can look at the book and you can have a nice derivation that does some things and this, that, and the other, and comes through with some terms. I think right now I should be your biggest hero because we didn't have to do that, but we still ended up at the place where we wanted to be. And so this is our differential term, a statement of Bernoulli. You'll notice that the differential term equals 0. And if we integrate this, because of the constant of integration, then this is the expression that we have. Written slightly differently here. I always write it in terms of dividing through by unit weights. Because then you end up with units of elevation, length, and all of these terms, since we're adding apples to apples, which we did 4 weeks ago and made sure that we understood that we're adding apples to apples and not apples to oranges. And so the units of these terms have to match. And so the usual way that I think of it is in terms of this expression here. Okay. It has to be written along a streamline. So it has to be the path that a particle of fluid will take as it goes through a system. And so what that physically means in this particular case is that if you write Bernoulli, you could write it at one point here, say point 1. You could write it at point 2 here. And that because it's constant along that streamline, then it has to be equivalent in terms of all 3 terms added together. But the proportion of those terms will change depending on what's going on. And so if you wrote those terms here, you'd end up with a fluid pressure which would be equal to this linear distribution of pressure as you go down here. You'd end up with a fictional location above here, which is due to whatever the speed of the fluid is that's going through here. And you're at some elevation between them. So you can always physically divide it between these 3 components. How high you are above a datum, where in this case 0 is equal to 0, z is equal to 0 on this point. This is the elevation head. This is the pressure head. The pressures will vary linearly down to that point. And since it's going at some velocity rather than being static, this is the velocity head that it has. If you deal with fluid flows in porous media, for instance, typically you'll work with what is referred to as hydraulic head H, which is equal to elevation plus pressure head. And you'll take the velocity term, which is usually small, and basically set it equal to 0. And so fluid flow in porous media is kind of that's why you're taking this class. If you're in petroleum engineers or environmental systems engineers, that's why you need to know something about fluid mechanics. So this velocity term will be very small. Velocities will be small. And so this term will be shrunk. But what you can think of it as you go downstream from this location to this location, the amount of energy that's held in the system, you can think of the sum of these 3 components as how much energy per unit mass there is in the system, stays constant as you go from upstream to downstream. And that's why this line is horizontal, and it's the same total distance between these. And as you go down to this point here, then depending on the location of the location of the point relative to the free surface, again, this would be the pressure head, and in this case, the magnitude of the velocity squared term. In this case, you could imagine that if this height is smaller, then you're having to squeeze the fluid through a smaller cross-section. If you pump the same amount from a big pipe that goes to a small pipe, then it has to accelerate. So v squared term has to be larger. And so there'll be more proportion is on this term. And so what it's doing is it's taking the energy and it's using the pressure energy and it's converting it to this v, or it's using elevation, if you like. The elevation's gone down. It's using it and converting it to overcoming inertia to be able to accelerate this particle from left to right. And so you can always think about it for that. Oh, I'm being hacked by the Russians. If you look at the bottom of the screen. So, okay. A pretty good exposition of this, I think, is this. This is out of the book, obviously. To look at those 3 terms. And so one way to look at those would be, for instance, to classify those terms in order, which are elevation head, pressure head, and velocity head. And relative to some datum, look at how those behaviors change for this very simple idea of a syringe that you're squeezing. And how do those individual components change? Well, at point 1, which is at the bottom, what do you expect? If you're sitting inside the syringe and someone closes it with your thumb over the end of the bike pump or the syringe, the pressure goes up. So you think that the pressure would be high. The velocity here is not moving anywhere. So it's moving maybe at the rate of the plunger, but it's moving very slow. So, sorry, I did that wrong, right? Wrong location. Pressure would be high, the second column. Elevation, it would be low. And v squared term would be essentially low or 0. I'm not sure how I'm using my symbols here, but you get the idea. This point here, what would we expect here? We know that fluid pressure acts all around at a point. We know that fluid pressure has to be atmospheric at this point. It's probably larger here. And so the fluid pressure would be relatively low, because now instead of being this elevated pressure, it's atmospheric. It's being squeezed. A small velocity here is being squeezed through a small orifice, so you'd expect that the velocity would be high, and, well, the elevation is still low. It goes up to the top of its arc, no different from this, right? No different. It's basically taken all of its potential energy or kinetic energy and turned it into potential energy. So the elevation is high, and this is low. This is really 0. So you'll note that even with my bad choice of terminology here, for each one of these we have one thing that's big at each of these levels. And that we can think of as the principal source of the energy in the system. Initially, we have pressure energy, which is stored strain energy, which is pumped into the system. We convert that into kinetic energy, which is v squared over 2g, rates of change of momentum or inertia or acceleration. And then ultimately, this kinetic energy carries us up to a top, and then we have some potential energy. So if you wanted to think about these, this is really potential energy, this is kinetic energy, and this is stored strain pressure energy. I'm not sure exactly what to call it. And so always think of these in those terms. And it's really not very different from partitioning these things between these 3 different components here. Let's do an example. So the example is, I need to do that. So actually it's right here. Actually, why don't we watch it again, just because it's kind of a nice thing to watch. We looked at this before. So what do we have in this particular case? We have a jet engine out here. It has some velocity coming out of it, and along a streamline, that energy hits the truck, and the truck flies off across the runway and into the bay, San Francisco Bay. And so how do we figure out whether that is a realistic scenario in terms of what we now are able to calculate? So if we had this system, let's see how good my drawing is. Pretty good, eh? Don't you think? Then what we're going to do is we're going to do 2 things. We're going to have an upstream location, and we're going to have a downstream location. I suppose we could write Bernoulli's equation in terms of ways that we think about defining it. between these two locations. Which is just this. We have our coordinate system, which is x and y, and importantly, z upwards. We know that we've forsaken this x and y because now we're interested in our streamline direction. So this is along a streamline. I missed an I in there, so you can see that. So this is along a streamline, 2 points along a streamline. And this, of course, is the velocity along the streamline direction. Happens to be the same. What do we have here? What do we know? Well, basically the same elevation. Airport runways are often horizontal. So Z1 and Z2 are equal. What's the pressure at this point? We made the point before that the pressure is atmospheric, point against this. So this, by our definition, if we take gauge pressure 0, atmospheric gauge pressure 0, then this is 0. But this is probably a big number because it's coming out of a jet engine. So this is a number we need to deal with. The velocity here, it's coming along at some big velocity, but it hits this, and as soon as it hits this, it's going to have to go around it. And in going around it, you're destroying the momentum of this. And so this velocity here, we're going to take as being 0. And we'd like to know what the fluid pressure is that develops. And so out of this, we're left with one expression, and that's that V1 squared over 2G is equal to P2 over rho G. Get rid of those. And this is going to be the dynamic pressure. This is the pressure that you get when I throw this ball at you and it hits you in the chest. You feel something. If the air comes at you at some velocity and all of a sudden you stop it and divert it around you, you're arresting its momentum. Rate of change of momentum is the deceleration, and that's the force that you feel. And so if we wanted to, I guess we could rearrange this and we could calculate what the fluid pressure is. P2 is going to be equal to velocity of the jet engine squared over 2 multiplied by density. So what are numbers that we know here? V1. It's coming out of a jet engine. Jets travel at 500 miles an hour. You don't know this yet, but you could rationalize that 500 mile an hour stream coming out of this will make the plane go at 500 miles an hour. And so V1 is of the order of 500 mph, which is about 250 meters a second, just because it's a 2-to-1 conversion. I just know that. Density of air, anybody? Ish. And so we could calculate the fluid pressure, as long as I haven't done anything wrong, as the pressure is equal to V1 squared, which is, I'm going to call this 100 meters as well. So 2 times 10 to the 2 meters per second squared multiplied by 1 kilogram per meter cubed divided by 2. And so this is roughly, well, it's going to be 2 times 10 to the 4 kilograms meters squared per second squared meters cubed. So if I get rid of one of these and one of these, then this is a kilogram meter per second squared, 1 over meter squared. And this is equal to, what's this? This is a definition of a Newton. And so this is 20 kPa, 20 kilonewtons per meter squared. So immediately we can calculate that the force acting on this truck is a pressure equal to P2, which is equal to this. And so now I suppose we have what we need if we wanted to calculate it. If we look at the broadside of a truck, this is the easiest way for me to think about it. Not a very good. So this is, say, 10 feet by 10 feet. I choose that because this is 10 meters squared, roughly. F equals pressure times area. So the force that's applied on this is equal to 20 kilonewtons per meter squared multiplied by 10 meters squared, which is equal to 20 kilonewtons. And so now, if you wanted to, you could do a very simple calculation. If I draw this in profile, these are the wheels for the truck. This is the truck. You have a force acting here of whatever this is. You have the weight of the truck. Resolve moments for the weight of the truck around about a meter's lever arm. You resolve this force around about a meter's lever, well, what it'd be FH. LH is equal to WLV. This would be LV. This would be LH. You can estimate these numbers. This might be a meter. These LH and LV are roughly the same order, and so you could figure out whether this is enough to be able to roll it. So maybe you should make the case that actually this multiplication is 20 times 10, so this is actually 200. So rather than being 20 kilonewtons, it's actually 200 kilonewtons. So that's even larger and therefore even more likely that it would be able to be rolled over. And maybe that large number comes from the fact that this area, 3 by 3 meters, is actually pretty big compared to the true line of the profile of the side of the truck. But regardless, just by using this balance, you can show that you have enough force to be able to topple it. Okay?